Okay, so let's move on and talk about psychophysics then. So psychophysics is essentially the pursuit of physical laws describing the relationship between physical stimulus and sensation. So again, this is another approach to the this black box problem. Okay, they're trying to find laws that connect the stimulus with the response. But it's something more specific than that. What they were interested in was when you increase the stimulus in some way, so if I make a sound louder or I make a light brighter, in what way does our perception of that stimulus increase? What's the relationship between the two? And Stevens in the 50s and popularised in the 70s argued that this relationship between the increase in the physical stimulus and the increase in your perception of the magnitude of that stimulus can be described by what's called a power law. Okay, so here's the power law. Don't be frightened by this equation. It's fairly straightforward. The italic I on the right-hand side here, this is the magnitude of the physical stimulus. So this is the thing that you can actually physically measure. So I can measure how loud a sound is or how bright a light is. On this side of the equation, you've got psi I, and this is your subjective sensation of the size of that stimulus. Okay, so on one side of the equation, you've got, if you like, how loud the sound is, and on the other side of the equation, you've got your perception of how loud the sound is. A here is an exponent which will be different. You know, what A is equal to will be different depending on the type of stimulation. So A will be different depending on whether we're talking about the brightness of a light or the loudness of a sound or whatever the stimulus is. In other words, the relationship between the magnitude of the stimulus and your perception of the magnitude of the stimulus will be different depending on the type of sensation. In other words, when I increase the volume of a sound or increase the brightness of a light, your perception of how much it's increased by will be different for the sound than it is for the light. And further than that, the argument is that if you know what this value of A is, then you will know what the relationship is between the stimulus magnitude and the perceived magnitude. K here, you don't need to worry about too much. This is just a proportionality constant. It just depends on the units of measurement that we're using for the particular sensation. So you don't really need to worry about this. Just think of it in terms of IA, so the magnitude of the stimulus multiplied by an exponent is equal to your physical sensation of that magnitude. Okay, so if we go back to this simple diagram again, so we know the size of the stimulus. Okay, that's the thing I can measure. And I can get you to rate your sensation of that stimulus. Okay, so for example, I could play you a sound, and I can get you to rate it on a scale of 0 to 100, how quiet or loud it is. And as I increase the volume of that stimulus, I can see how your sensation rating changes. And if I do this enough times with enough people, then I can calculate what A is. I can calculate how generally people's sensation of a stimulus increases as I increase the actual stimulus magnitude. So let's look at some examples. Let's look at loudness, okay, this example. For loudness, if you conduct this experiment, you find that the exponent A is less than 1. And what this means is that when I increase the volume, to start with, your estimation of it increases quite rapidly. But after a certain point, I have to massively ramp up the volume for you to perceive any increase in loudness. If you like, it's kind of a diminishing returns. Okay, and we know this is true for loudness. You're very sensitive for small changes at low volumes, But at loud volumes, you need massive changes in order to detect any difference. Let's look at an opposite example. So this time I'm going to give you pain. I'm going to give you an electric shock. Okay, and for this, A will be larger than 1. And what this means is that for every little increase in the electric shock, your perception of the pain is going to go up massively. Okay, so this is the opposite of what the example with loudness. If A is equal to 1, an example of this is time perception, more or less, then there'll be a linear relationship between the increase in duration, or the increase in the stimulus, and your increase in the perception of that. So if I double the duration to be timed, you'll perceive it as being twice as long. There's a linear relationship between the two. So now that I've told you this about how this function alters depending on the value of A, then I don't need to keep drawing a graph every time. Okay, if we look at all of these different types of stimulus, we can see that for each of them there's a particular value of A. And from what I've told you, you now know that if the value is less than 1, then it's going to be a function similar to what we saw for loudness. If it's a value of 1, then you know that it's going to be a linear relationship. And if it's a value that's larger than 1, then you know it's going to be an exponential relationship, like we saw for pain. Okay, so for example, here for visual length, we can see that A is equal to 1. So without, I don't need to draw you a graph. You know that this is going to be a linear relationship. If we look at electric shock here, it's got a massive value of 3.5. So I know that for every little increase in the electric shock, your sensation rating of it is going to be massive. Or we can look at brightness, for example. It has a less than 1. So I know that I'm going to have to ramp up the brightness a lot for you to get to perceive any increase in brightness once we've got over very low levels. The other thing that psychophysics or psychophysicists are interested in is sensitivity. And we have two ways of measuring this: variability and threshold. So classical experiment psychology is interested in thresholds and variability, and they're both measures of sensitivity, but they get used in slightly different situations. So a threshold is, there are two types of threshold. One is an absolute or detection threshold. So how loud does a sound have to be for you to be able to hear it? How bright does a light have to be for you to be able to see it at all? The other type of threshold is a difference threshold. So, for example, if I've got two sounds, how much louder does one sound have to be than the other for you to be able to tell the difference? And these are the two types of thresholds that we commonly look at. And in fact, we most commonly look at difference thresholds. Variability is something slightly different. This is the dispersion of estimates around the mean. So, in a way, you can think about this is how variable the system is, how much noise there is in the system. Yeah, for example, if I gave you the same loudness several times in an experiment, how consistent is your perception of that loudness? Is it all over the place, or do you roughly give me the same magnitude estimation each time? Okay, and you can see where this type of measurement can be very useful. Okay, if we're interested in, for example, a patient group versus a control group, and we think that the patient group, for some reason, are worse at some particular perceptual domain, let's assume that they're worse at time perception, then a simple way of measuring this would be to look at their difference threshold. You know, are they worse at detecting differences in duration? Yes or no? And there's a way of looking at this. However, when we look at thresholds, we also need to bear in mind something called Weber's law. Okay, Weber was German, so you see it written as Weber. The correct pronunciation is Weber. So Weber's law, in a nutshell, is saying that the just noticeable difference in stimulus magnitude is a constant fraction of the mean. Okay, that actually sounds more complicated than it is, but what it means is that your difference threshold, the point at which you detect a difference between the loudness of two notes, for example, will be dependent on how loud those notes are to start with. So your threshold is dependent on the stimulus magnitude that you have in the first place. And this can be expressed as an equation. And essentially, it means that the just noticeable difference remains a constant fraction. It doesn't remain constant, but it remains a constant fraction of the stimulus magnitude. It's easiest if we work through an example. So a simple example is the detection of differences in weight. So if you lift up and hold a weight of 2 kilograms, you'll notice that it takes some effort to hold it. If you add to this weight another 5 grams and lift it, you may not notice any difference. You won't notice any difference at all between the apparent or subjective weight between the 2 kilogram and the 2.05 kilogram. But if I keep adding weight, you'll find at some point you notice that it's heavier. So let's, for example, say that we will notice there's a difference when the additional weight is 200 grams. So the increment threshold, or the difference threshold for detecting the difference between a 2 kilogram weight is 0.2 kilograms. This is the just noticeable difference. Okay, if I start off with a 2 kilogram weight, so now let's look at the equation. I is the stimulus magnitude. Remember, I start off with a 2 kilogram weight. If you see a triangle like this, it means change in. So the change in the stimulus magnitude that I have to have in order to detect a difference is 200 grams. Okay, I started off with a 2 kilogram weight, and I only noticed that it was heavier when I increased the weight by 2 kilograms. If I divide one by the other, this gives me a constant 0.1. Okay, so we're arguing, or Weber's law is arguing, that regardless of how large this stimulus magnitude is, when I work out what the just noticeable difference is, it will be a constant proportion of it. Let's look at an example to see whether this is true. Okay, so now we're going to repeat the experiment again, but instead of starting with a 2 kilogram weight, we're starting with a 5 kilogram weight. And again, we keep adding weight to it until we notice that it's increased in weight. This time we find that it takes 500 grams, or half a kilogram, before you detect a difference. So if we plug this into the same equation, okay, so I is the stimulus magnitude, remember, in this case it's 5 kilograms. Our change in stimulus magnitude that we need to detect a difference is 500 grams. I divide one by the other, and I get the same number that I got before, 0.1. So it's remaining a constant fraction. The just noticeable difference is remaining a constant fraction of the mean. Okay, so if I plot the intensity of the stimulus against the difference threshold, or the just noticeable difference, it remains a constant fraction. Okay, if I double the weight, I double the just noticeable difference. So if I divide one by the other, I'm always getting the same number. Just to make things confusing, the just noticeable difference is also called the difference threshold. It's also called the increment threshold. It's also called the difference Lyman, but it's simply a measure of sensitivity. In some other situations, a measure of sensitivity is the standard deviation, or the variability, which, for reasons I won't really go into here, it tends to be a more useful measure for time judgments. Okay, so that's difference threshold, but we also have absolute thresholds. So this is that the size of stimulus magnitude that's necessary for you to even be able to detect the stimulus in the first place. Now these are based on certainty, and normally they're based at 50%. Okay, you can imagine if I played a very quiet note, sometimes you'll be able to hear it, sometimes you won't. Okay, so we need to set that threshold at some level of certainty. And normally we set it at 50%. You can imagine it, if we set it at 100%, then that volume is going to need to be a lot louder. Okay, if we want to see how loud a noise has to be for you to detect it 100% of the time, then it's going to need to be a louder noise than if we set it at 50%. And the convention is normally 50%. Typically, we don't tend to deal in absolute thresholds in psychology, but these have been worked out historically. And they're quite poetically expressed. So for the detection rate for hearing, it's a tick of a watch in quiet conditions at 20 feet. I mean, obviously all of these have been measured in absolute stimulus magnitudes, but they're often expressed in this way, which gives you a kind of better handle on it. So for vision, the absolute threshold is the flame of a single candle at 30 miles, which is pretty impressive. Touch is my favourite. The wing of a fly falling on your cheek from 1 centimetres. Okay, but we don't tend to use these as much. Just go back a second. So just to reinforce why Weber's law is important, because the difference threshold is a constant fraction of the mean, it means that if we go back here, if we're interested in measuring a difference threshold for a particular stimulus, then the difference threshold that we measure will be dependent on the size of the stimulus. Okay, so the larger the stimulus I use, the larger the difference threshold will be that I find. So difference thresholds are relative to the stimulus magnitude. Okay, so how do we determine a difference threshold? Well, there are many ways of doing this, but I'm going to show you the simplest way, and you'll find that all of the ways of doing this are just variants on this this threshold technique, and it's called a staircase threshold technique. And it's incredibly simple. So on each trial, 2 stimuli are presented, a standard and a comparison. And the subject simply has to decide which is louder, brighter, sharper, bluer, longer, whatever the stimulus domain is. If they get it correct on that trial, then the difference between those 2 stimuli on the next trial is decreased. Okay, so let's say we're talking about time here. So I play you 2 notes. One is longer than the other one. I ask you which is longer. If you get it correct, then on the next trial, I'll reduce the difference between the lengths of those 2 tones and see whether you get it right. If you get it right, I'll reduce it again. And I'll keep doing this until you get it wrong. If you get it wrong, then on the next trial, n+1, I'll increase the difference between those 2 tones. So this procedure hunts out how different the 2 notes have to be, or 2 stimuli have to be from each other, for you to be able to detect the difference. And we typically do this for, say, 50 trials, and our threshold measure is the mean difference between the 2 stimuli over the last X trials. Typically, if it's a 50 trial, then it would be over the last 20 trials. However, there is a problem with this. If you think about this procedure, okay, if you think about each individual trial, I present you with 2 tones, 2 stimuli, and I ask you which is longer. Now, even if you're not paying any attention, even if you're completely insensitive to duration, you're going to give me an answer. You're going to give me a guess. And on each trial, you have a 50% chance of making a correct decision, regardless of perception. So for difference thresholds, we're not really interested in thresholds that are around chance level. Okay, we're interested in thresholds that are higher than that. So what we need to do is change this technique to set the threshold at a higher percentage of this. Okay, if we leave everything the same, then what we're going to find is a difference threshold, how different those 2 stimuli have to be for you to be able to detect the difference 50% of the time. But typically we set it higher than this. We're not interested in chance level thresholds. And the way we do this is we change our methodology slightly. So this time we're going to punish, in inverted commas, more for an incorrect answer than we reward for a correct answer. In our first example, so if you got it right on one trial, for example, we would maybe decrease the difference between the 2 stimuli by 200 milliseconds. If you got it wrong, we'd increase it by 200 milliseconds. So it's the same step we're using both up and down. But this time we're going to do something slightly different. We're going to change the ratio of this step. So we're going to if you get it wrong, we're going to increase the difference between the 2 stimuli by, say, 2 or 3 steps. And if you get it right, then we're just going to be reduced by 1 step. And the way we calculate this ratio of steps is by using this formula here. So for any equilibrium point is the percentage at which you set this at. Okay, so in this example, we're not interested in 50%, we're interested in 75%. But if we did use 50% and we plugged 50% into this equation, what it would give us would be a 1-to-1 ratio between the step up and S step down. So S up here is the step up, so how much you're increasing the difference. S down is how much you're decreasing the difference. P is our probability point. Okay, so if you plugged in 0.5 here for 50%, you'd end up with a 1-to-1 ratio. But we're interested in something else. Usually we determine difference thresholds at the level of 75%. So we need to calculate, we're trying to find out how much do two stimuli have to differ by for the subject to discriminate between them 75% of the time. So our XP is 75, okay? That's what we're trying to find. So we're going to plug that into this equation, okay? I'm hoping that most of you have a reasonable grasp of how to plug things into equations. But quick spoiler, this is something that this is one of the things that I'll be potentially testing in my part of the exam. Okay, so I might give you a threshold value. Okay, it probably won't be 75 because that's the example here, and I'll ask you to calculate what the step up and step down is. But hopefully, if you go through each part of how I've solved this equation, you'll see how eventually you end up with a 3-to-1 ratio. Okay, so I now know that if I wanted to find a difference threshold at 75%, every time people get it wrong, I need to go up 3 step sizes. Every time they get it correct, we need to go down one step size. However, again, remember Weber's law. The threshold will also be dependent on the standard that I use. It'll be dependent on the duration that I use on each trial. Okay, on each trial there's one. You're presenting 2 stimuli, but one of them is always remaining the same duration. Okay, so in my example, in every single one of those 50 trials, you're being presented with a, say, half-second tone. That's the standard, and it's the comparison, the second tone, that I'm changing the duration of to make it more or less similar to the standard. On each trial, we randomize the order, okay? So people won't know which one is the standard, which one is the same on each trial. But what I decide to set that standard as will determine the difference threshold that I eventually find because of Weber's law. Now, the usefulness of this technique is that it's widely accepted. There are other variations of it, which you may have heard of. Best Pest is an example, where it uses a more complicated equation. It looks for places where reversals, where people go from up to down or down to up. And essentially, what it's trying to do is get to the threshold more efficiently than giving them 50 trials. But actually, it doesn't actually take that long to administer 50 trials, depending on what the stimulus is. Now, why this is useful, and this is kind of the thrust of some of what I want to talk about today, is that if you're aware of these techniques, then you can bypass a lot of arguments with referees or people marking your work or people at conferences. You can bypass a lot of arguments about methodology. And there's an example of this. So this is a paper that I published quite a few years ago now. Visual and auditory timing had been investigated to quite a large extent, but hardly anybody had looked at vibrotactile timing. So I wanted to investigate how good people were at timing vibrations on the skin compared to timing lights or sounds. Now, if I wasn't aware of psychophysics, there's any number of tasks that I could have given them and tried to measure how good they were, how good their performance was. But we didn't do that. We thought, okay, let's think forward to the referees. We don't want any arguments about methodology, so let's use a simple staircase threshold technique, and let's zero in at the threshold at 75%. And that's what we did here. So you can see at trial 1, there's a difference between the standard and the comparison durations of 30 milliseconds. This is the average data. If you looked at an individual's data, you'd see that it kind of bounces up and down. This is the average data. But you can see that it levels out. It finds the difference threshold. And you can see that it's highest for visual, lowest for auditory. Okay, so highest means worse. It means you need a larger difference to detect the difference. Again, this is something that people often get confused about when they're seeing threshold values. They think a large threshold value is better. It's not. A smaller difference threshold is better. So you can see for the auditory, you need less of a difference to detect a difference. And we found that vibrotactile was somewhere in between the two. So although we had arguments with this paper, we didn't have any arguments about the methodology.